Okay, let's continue the discussion of R. Uh, Before we state the proposition 1.4, the R is called the radius of convergence of the power series. The radius of convergence. Okay. The radius of convergence. Okay. Okay, now let's talk about the proposition 1.4. The proposition 1.4 provides another possible way to compute this number, radius of convergence. So if series a sub nz minus a to nth power is a given power series, with radius of convergence r, then this r is also equal to the limit of the ops value of an over an plus 1. Well, this limit may not exist. We say it is equal if this limit exists. If the limit exists, then it is also equal to r, the radius of convergence. Okay, so see the proof. Again, we assume a equal to 0. When we state the theorem or proposition property, we always state it in the most general way, so z minus a. But when we prove it, because it's not that important to have a or have no a, so we always assume a equal to 0. Okay, so the theorem works for the most general case, but the proof is common with or without a. And let alpha be this limit. Okay, so we already assume this limit exists. We call it alpha. And then we are going to show that this alpha also satisfies condition A and condition B in the previous theorem. Okay, we are going to claim alpha satisfy condition A, condition B. So there's only one R. Only one R satisfy that, then R is equal to alpha. R is unique. The radius convergence is unique. So that's why we have this. Okay? So we show that alpha satisfies A and B in the previous theorem. Hence, R is equal to alpha. Okay, so now let's see. First, suppose that ops value of z is less than r less than alpha. Whenever it's small. Basically, suppose z is less than alpha, then we insert a little r between those two numbers. Every two real numbers, there's always a third real number between them, right? Okay, then we find an integer capital N such that R is, you see, alpha is greater than R. So R will be less than ops value of an over an plus 1 for all n greater than or equal to capital N. For sufficiently large n, this number will be very close to alpha, so it will be greater than R. Okay? Be greater than R. So now let B be A sub capital N, this capital N, and R to the power of capital N. A sub capital N ops value R to the power capital N. Okay. Then let's continue to check the next term. Next term, A sub capital N plus 1 and R to the power N plus 1. It is AN times R to capital N. Okay, and this one is what? This one is less than. If you move this to the left side, it's less than or equal to. You can put equal or you don't put equal. It doesn't matter. So ops value of A sub N, R sub N. All right, so this is B. You see what I do? So here, use this condition. And then you can consider the next term. A sub N plus 2, R to power N plus 2. First, N plus 2, R N plus 1. And again, this one is less than A N plus 1, R N plus 1, and we just show it is less than B. Okay, so for all sub N, so for all we get what? We get ops value of A n R to nth power ops is going to be less than or equal to B for all n greater than or equal to capital N. We start from capital N and continue it infinitely many times. All right, so this is for R. Now let's see the. Then what we have? A n z to n. A n z to n ops value is equal to A n R to n times z over R to n. And this one is less than or equal to B times z over R to nth power for all n greater than or equal to capital N. See? So this is a constant number. This is our geometric series because we assume this ops value of z is less than R. It's a geometric convergent series. So it's not ops value. It's just a parenthesis. It's absolutely. So this series will converge absolutely. And the original series is dominated by this absolute convergent series. So it converges absolutely. Right? So it converges absolutely. For whatever R, less than alpha, the series A n z to n always converges absolutely. we can get alpha should be less than or equal to capital R. If alpha is greater than capital R, then there's some, see, this is R. If alpha is greater than capital R, there's some point little r here, then you will get at least absolute convergence for this R. But this R is greater than capital R. It does not follow the conclusion in a previous theorem. So that's why this alpha must be on the left side of capital R. Right? So this is the wrong case. That's why we get alpha less than or equal to capital R. Okay, this is actually the part A. Part A. And on the other hand, we're going to talk about part B, divergence. If upper bound of z is greater than r greater than alpha, upper bound of z is greater than alpha, then you insert r between them. Then upper bound of an over an plus 1 will be less than r. This implies like this, right? So this ratio will be close to alpha. When it is close to alpha, it's less than r. When it's less than r, you move this upper bound of an plus 1 to the right side. It's like this. It's inequality for all n greater than or equal to certain integer capital N. Then like this process, this process we have equality. Only this place we have inequality, and this inequality comes from here, comes from this condition. So like the previous estimation, we have what? We have upper value of an r to n is going to be greater than or equal to b, where this b is upper value of a sub capital N r to power capital N for all n greater than or equal to capital N. See it? That's this way, right? So here is less than because this part is less than. Here is greater than because this part is greater. And this gives us the upper value of an zn is equal to an rn z over r upper value to nth power, and this one is greater than or equal to b. And remember that this upper value of z is greater than r for all n greater than or equal to capital. All right. So see, this one is again is a geometric series, but it diverges because it's greater than 1. This ratio is greater than 1. It diverges. This term becomes unbounded. This term becomes unbounded as n approaches infinity. Hence this series an z to n diverges. And z to n diverges. And r greater than alpha is arbitrary. This implies that this alpha must be greater than or equal to r. Alpha is less than or equal to r. Alpha is greater than or equal to r. This is part B. So alpha is equal to r. See it? So this is a very, very interesting and short, neat proof. You're supposed to memorize it. It's a very, very good proof. It tells us how we can compare these two numbers. These two numbers. It's very good. Very, very good. Okay. With the help of this proposition, we are going to have our second important example. So now we consider the power series. Series n from 0 to infinity, z to n factorial over n factorial. Okay, in this case, a sub n is 1 over n factorial and a is 0. And then let's check the limit n approaches infinity. 1 over n factorial over 1 over n plus 1 factorial. Remember, this is a n over a n plus 1 with ops value, but this is a positive coefficient, so I don't put a ops value. After you cancel n factorial from top and bottom, you get a limit of n plus 1 is infinity. So R is infinity. So we get the radius of convergence of the power series infinity as infinity. R equal to infinity. So it means it converges at every complex numbers. So converges at every complex number, and it uniformly converges on each compact subset of C. Well, it's not just compact. Each bounded subset, it is uniformly converges, because when it is bounded, it can be covered by an open by a closed disk. Okay, it can be covered by a disk. So that's why it's a uniform convergence. And because for every z, this power series will give us a number. It will converge to a number. Then we define this as a function, and it satisfies the property of the exponential function. So we give it a name. We define it as e to z, or sometimes exponential of z to be something like this. Okay, the exponential series or exponential function. The exponential function. Exponential function. We will see the reason why it is an exponential function. All right, so this is the first lecture. It's a short, and it contains the information about the course. Anyway, we just start our first topic, the power series and its radius of convergence. From that part, we gave our second example. The first example is a geometric series. Geometric series is simple because it has a very, very neat, powerful summation property. Remember that as a we have this multiplication property. From this property, we can sum this series as a ratio. But not every power series has such beautiful summation property. So we have to study the radius of convergence and stuffs. And from the radius convergence, one is the definition, the other one is the proposition. From the proposition, we get this exponential function. The proposition is used widely because the proposition is easy to compute. You just compute the limit of the ratio an with an plus 1. The definition is also useful, but you have to compute the lim sup, which is a little bit complex than the regular limit. So that's why we apply the proposition. Okay, so with this, at this moment, we finished the first lecture. These two videos, one is long, the other one is short. It will cover the one lecture. Every week we have 2 lectures. Okay, so every week you will expect 2 long videos and 2 short videos. Okay, okay, so total it will be more or less like the 2 hours 40 minutes. Okay, thank you very much, and we will continue the discussion in the next video. If you have any questions or I make any mistakes in the writing or the explanation, just send me email. I can correct it. Okay, thank you. Bye bye.